So we're starting with the first question here. I should have set this up earlier. Well, we got, with the antihistamine Seldane was introduced, it was heavily promoted because it supposedly did not cause drowsiness, unlike other antihistamines. A portion of the prescribing information for the drug is taken from an advertisement. We have for Seldane, 9% of the 781 people in the sample reported drowsiness. And for the placebo, 8.1% of the 655 in that sample had, what is that, drowsiness. So our question now is the proportion of Seldane greater, the proportion of patients reporting drowsiness greater than the patients reporting with a placebo? Okay, so let's check this out for question 10 then. So question 10, we are talking about a P this time and not a mu. So the P is going to be equal to the proportion of patients reporting drowsiness using Seldane. Null hypothesis. All sorts of problems. That's going to be at the, well, we want to test it against a placebo, right? So we want to see if it's greater than the placebo. Why does my chair feel lower than normal? Like the spring deflated or something. So this is admittedly a little strange, but we want to say that the proportion is the same as the proportion of people who are drowsy using Seldane, the 0.81. Oops. The next one is the alternative hypothesis. The alternatively, we want to know, is it greater than 0.081? Okay, that's true. Then we got to go with our things about our sampling distribution. So number one, our sampling distribution. Sorry, what am I doing here? Mu of P. That's going to be 0.081. 2. Sigma of P. That's going to be equal to the square root of 0.081 times what is that, 919, divided by our sample size, and our sample size is 781. 0097. Let's keep that as 0097. 3. We have a normal sampling distribution, or approximately normal sampling distribution. Okay, so let's figure this out. We have N times P. That's equal to 0.081. Sorry, 781 times 0.081. 63. That's definitely greater than 10. Then we have N times 1 minus P. That's equal to 781 times 0.919. That's definitely greater than 10. We have that approximately normal sampling distribution now. Nothing else to test. So now we can just go ahead and figure things out. The first thing we're going to need is, well, the p-value. That's going to be equal to the probability that a p-hat is greater than, and what are we getting, 0.9? And that's equal to the probability.
9 or 0.0?
0.09, you're right. That's a probability that z is greater than, we should normalize that, right? So that's 0.9 minus 0.081. 0.09? I did it again. Divided by 0.0097. That's going to be equal to the probability, the p-value equals the probability that z is greater than this number here. And calculate that. What did we do? 1768. So which means our findings are not significant. Since the p-value is greater than alpha, supposing alpha is 0.10, maybe we should put that a key beginning. Supposing alpha is 0.10, since our p-value is greater than alpha, okay, we fail to reject. Null hypothesis. What does this mean? The data does not support that Seldane users experience a higher percentage of drowsiness than placebo users. That's kind of nice, right?
Yeah. Did we use the, can we calculate the signal if we use the population size of the Seldane?
No, we use the population size of the Seldane. Not the population, the sample size for the Seldane. Yeah.
Yeah.
Because our sample is a sample of patients who use Seldane.
Right. Okay. Isn't that standard deviation? Doesn't that apply to the placebo? Because you're talking about 0.0.
No, we're assuming that the placebo is like the normal population. And in the normal population, then approximately 8.1% are going to experience drowsiness. Okay, this is actually a weird question. So, any problems with that?
So p-value is the chance of our test statistic occurring.
Yeah, technically our test statistic or something more extreme.
Or something more extreme than our test statistic occurring. And so Yeah, okay.
So since our test statistic isn't all that rare, or something more what's the word I'm looking for? More extreme than our test statistic. Since it's not actually all that rare, then we can't say that our sample is inconsistent with a hypothesis.
Because our alpha is 0.10, so that's the chance we want to take
Mhm.
that it could be.
This is when you think about it, 17% is pretty high probability that you
Yeah.
will. And it makes it's kind of common to find that.
Yeah.
But if it's under 10%, then that tells
Then
you
that's then we're saying if it's below 10%, then that's not very common.
It's not very common
And so we
if the null hypothesis was
is
true.
Yeah. Mhm.
Okay? All right, so let's get to that third one then. Free response 3. Did I write free response 2 up here? No, I didn't. Did I write it 10 here?
I don't know.
Free response 2. Okay, so free response 3 says 16 students in the 2011 AP Stats class period 3 had the following scores on the chapter 12 test. If I remember correctly, these are actually the scores. There were only 16 people that year. Yeah, 2011. Okay, and does this sample confirm the mean test score for chapter 12 for all students is 500? Greater than 500. Okay.
Is it out of 1,000?
Yeah, out of 1,000.
So that person got 950. So only one kid did really well.
Yeah.
Someone else had 215.
Yeah, that's a pretty low score. So what is our population characteristic? Population characteristic. Well, our population characteristic is a mu, right?
Yeah.
And that's going to be the average among.
So you just need to put this in the calculator.
Among chapter 12 test takers in AP Stats. And what's the next thing here? The next thing we have is, what are the hypotheses? Okay, that's pretty fair. So mu H naught would be mu equals 500. H alternative would be mu is greater than 500. Nice. B, does the data deviate from normality? Comment on the 3 graphs. Would you use T procedures or Z procedures? Okay, so does this deviate from normality? Well, it's a small sample. First of all, I could probably tell you immediately that T procedures are appropriate. There are a couple of reasons why. Number one is the population standard deviation. Yeah. Must be estimated with a sample standard deviation. Okay. So that's the big reason. Number two, another reason why is the sample size is small. Small. N equals 16. So those are two big reasons why you want to use a T distribution and not the Z distribution. Okay, so does the data deviate from normality? Now we got to actually look at those graphs, at the graph. So I'll be putting those in shortly. Okay, so there are 3 graphs that you could look at here. And we'll go through each of them as soon as we get the data here. 500 and 500, 481, 723, 850, 504, 542, 596, 265, 400, 215, 735, 950, 654, 608, 315. So that's all of our data in there. Okay, so let's take a look at our graphs. Then the first graph that you probably want to look at is the histogram. We'll look at a histogram of list 1. Don't have to make a big deal about it, just use Zoom 9. There we go. That looks pretty centrally weighted to me. Okay. It does represent some skew. You're right there, but it doesn't look like it's not centrally weighted. Okay. Let's see. Okay, so histogram looks centrally weighted. It's not, does not look symmetric, but it does look mound shape, right? It does look mound shaped. And that's really what we're looking for. We're just looking for a mound shape. Okay, next one that we're gonna look at is the box plot, and in particular, we're gonna look at the box plot with outliers. And the main reason we're doing this check is to see if there are outliers. We're gonna change that. Oh, look at that, no outliers. Okay, so maybe we should get rid of that other graph. What is that other graph? Oh, why is it still going? Ooh, why is it still going? Here. Graph. Done. Great.
Yeah.
Second graph.
So sometimes you're gonna have to zoom out a bit to see if there are outliers.
Well, if you push Zoom data, Zoom 9, you won't have to do that.
It'll show you that.
It'll show you everything if you use Zoom data. Okay. So what are we calling this? The box plot confirms central weight and that. How should we write this? And confirms and
Confirms that there are no outliers.
That's good. Lack. Box plot confirms central weight and lack of outliers. Great. Last one we want to look at is we're going to look at the normal probability plot. Remember, with this one, we're just looking for it to be close to linear. That's pretty good. I probably should have Zoom 9'd it. Zoom 9, there we go. Okay, it is easy. You can see a curve here, but it's not an extreme curve or anything like that. So this looks, you know, pretty linear, or approximately linear. So you should feel safe using t-procedures with this data. This is a normal probability plot. Looks approximately linear. One is safe using the t-procedures. No problem, use t-procedures. It doesn't say to do this, but we're going to go ahead and finish this off, okay? So this is, how do we write this? Below work is not asked for in the question. But we are doing it anyway. Okay, so we have our null hypothesis, we have our alternative hypothesis. We're ready to go with number one, which is center mu of x bar. And that's equal to 500. Number two, sigma of x bar. That's going to be equal to this, the sample standard deviation over square root of n. So we should figure that out. So our calculator from the stat menu tells us L1 has a standard deviation of 214.7. 214.7 divided by the square root of 16, about 53. Lastly, we have a small sample. So what are we saying? Sampling distribution is approximately normal because, number one, small sample. That is centrally weighted with no outliers. And that's all we have to write. Okay, so now we got to do our work. Our p-value is going to be equal to the probability that we have a x bar. What was our alternative? Greater?
Yeah.
Greater than 500? Probability that x bar is at least as extreme as 574.3. And that's going to be the probability that t with 15 degrees of freedom greater than 574.3 minus 500 divided by 53.6. 675. Create.
That's
Create. You're right. P-value is equal to the probability that T is 15 degrees of freedom. It's greater 1.384. Mode?
Yeah.
TCDF. Did you get one? 39? 10% alpha, right? Using alpha equals 0.10. Since the p-value is less than alpha, really close, we reject the null hypothesis. So what are we concluding? We say the data supports the mean chapter 12 test score among stats students is greater than 500. It was really close though. I feel very unsure about it.
When we're using T and Z scores, should we just round to
Only for tests, I usually round those to 3 decimals. I don't think anyone's really going to worry about where you round it as long as you don't round it to the 10th place.
Yeah.
So you could go just to the 100th place. It's not going to be that big a deal. Okay. Any questions? Yeah.
When you compare it to the value of alpha, is it basically, because you're assuming the null hypothesis is true, is it basically kind of like saying like alpha is the amount of like percentage, like alpha is the percentage of chance that of like having an error that is like acceptable, and then like so if you're going over it, then like you have to fail.
Have it less than it is.
Yeah, less than.
Less than it is where you're like, okay, this
So
is
the null has,
Yeah.
the data supports the null.
If it doesn't pass alpha, it's like
Oh, the
saying
da-
you're
when it
90%
doesn't support
confident.
it, it's less than.
It's like saying we're 90% confident that we can reject the null hypothesis.
Right.
Is that right?
I'm not sure I would ever say it that way.
Yeah.
Bye-bye.
When would we ever use not equal for the like alternative hypothesis?
Well, in this, I mean, if we were going to take this problem that we were just talking about, you could use a not equal sign for the alternative hypothesis if the question was phrased, does the data confirm, or does the data confirm that the mean score is 500?
Oh, and then if it's less than, then we would use the less than, but since it was greater than, we use greater than.
Yeah.
Okay.
Anything else?
Can you go over again how, I know we were talking about in class about
Mhm.
when we use like the T procedure and when we like, we were saying, like,
Sure.
I don't know, it was getting confusing when Josh was kind of talking about it and like, I didn't understand.
Okay, so use Z. Okay. If the population characteristic is a proportion. Two. if the population characteristic is a mean, but the population standard deviation is known. Oh, that should be and. 3, use a z if the population characteristic is a mean and the sample size is large, very large. This is actually rare. This one's also rare.
If
In fact, I'd say that second one is unrealistic. If you're trying to measure the mean, but you already know the standard deviation, if you know the standard deviation, then you pretty much should know the mean.
But if we have that mean,
Mhm.
that's for number 2. If we have the mean and the population standard deviation, but we still have the sample size that's smaller than 30, does it not matter because the sample should be normal if the population is normal?
Yeah, it shouldn't matter.
So it doesn't matter. The sample size doesn't matter in that case. You should still use either give the population.
Yeah. Use T. 1. Population characteristic is a mean, and the standard population standard deviation is unknown. 2. Population characteristic mean, and the sample size is small. Yeah, that's it. Typically speaking, if you're going to be talking about a mean, population is a mean, or the characteristic is a mean, then you should be using a T. And then if the population characteristic is a proportion, you should be using Z.
Okay.
So it's almost an exact dichotomy. Almost. Okay, let's turn this guy out.
So I guess the last part of that, number 2,
Sorry.
then,
Mhm.
is technically population characteristic is a mean and sample size is small unless you have the population standard deviation.
I would probably,
Well, what were you saying?
I can't imagine that ever really happening, is the thing.
What was Josh saying when he said like you should just use it?
He was saying pretty much it's kind of the same thing I'm saying. It's
Okay.
a dichotomy.
Okay.
The proportion uses Z,
Mm-hmm.
mean uses a T. You'll never be wrong if you do it that way. Okay.
Oh, can you show number 11? Because I don't know if I finished.
Sure. 11, suppose you select a random sample of 5 from a normal distribution with an unknown mean and an unknown variance. Null hypothesis, mu is 65, tested against mu is greater than 65 at a 5% alpha. The resulting mean is the 5%, as the resulting sample has a mean of 68.25, S squared is 9. What is the appropriate test statistic, rejection region, and conclusion? Okay, so
Yeah, just
for 11, what we're saying is that you should be using a T distribution. You're looking at a mean, right?
Yeah.
with an unknown standard deviation. All we need, I mean, unknown population standard deviation, boom, you got the t distribution. Okay, so the test statistic, that's going to be equal to the normalized sample data. So normalized sample data, that would be 68.25 minus 65 from the population standard deviation, divided by, and then here we got a sample is 3 for our S, and then square root of 5. You know what I'm going to do? I'm going to do this. I'm going to write down the sigma x bar. Do that first. That's 1.34. We'll just put that down here. So that's our test statistic, 2.425. This next thing is the rejection region and the conclusion. So our rejection region, since we have an upper tail test, what we're looking at is, draw, this is nice. Looking at a, where's my cursor? What happened here? So we're looking at a normal distribution, normal curve here. That looks horrible. We're saying that the rejection region should have an area, an upper tail of 0.05. Okay. So to get this, we're going to use inverse T. We'll use the probe. If I don't have the program, then I'm going to use the built-in calculator function. Let's see if I have the program for inverse T. I do. Number 5. Inverse T, we're doing inference here. We're going to do one tail. Alpha level is 0.05. What's our degree of freedom? 4? 4. Now that's 2.132. Okay. Now remember, it's always going to give you the positive. So if you were going to do a left tail, then the correct T here would be negative 2.132. This program, however, only gives you the positive tail. So we got 2.132, 2.132.
This is the negative relation?
No, upper tail. So what we're saying then is we're going to reject the null hypothesis if the test statistic is greater than 2.132. Because I say that because look what happens to our test statistic. We have where's my cursor? We have here test statistic of 2.425. Where does that lie?
It lies.
Yeah, 2.4, it's got to be to the right here. T equals 2.425. So we're in the rejection region. Our alpha level here, or this is going to be our p-value. Our p-value is going to be less than 0.05. So we should reject our null hypothesis. So the correct conclusion would be we should reject the null hypothesis since 2.425 is greater than 2.132. We reject the null hypothesis. Which means the data supports the alternative hypothesis, whatever that alternative hypothesis is.
Or we could have just shown those.
Yeah, or we could have just done the p-value here. Okay. All right. Shut her down.